Okay, we can start. Yep. Hello, everyone. Welcome to the course Automating GIS Processes Part 2. Many of you are continuing this course, like have taken the first part in first period. And I know there are also some students who have not taken part in the first period. So we will have a bit of introduction through which you will get to know about what we are going to do in this period, in this course. For those of you who have taken the first part, some of the things I covered today, you know them already. So, but it won't take so long. So, yeah. So usually we don't have a slides. We just do things. We do coding, same as first period. But now it's the first lecture, so I have a bit of like introduction slides. For your information, I'm recording the lecture, but I want you to also be active. It's a smaller class compared to the first period, so I'm hoping that there will be a bit more discussion. If at any point, I hope recording doesn't stop you from being active. And if you want to be excluded from the recording in case you have talked here or I don't know, just let me know and I can cut it out from the video. But yeah, the idea is that smaller class so we can have a bit more discussion around things. Yeah. My name is Kamiar, or just Kami for short, and I'm a lecturer in geoinformatics here at the Department of Geography. I have a background in geoinformatics from Aalto University, and I've been teaching this course now for 3 years. So, continuing with introducing myself. Yeah, so I studied geoinformatics. I come from a technical background, and I will tell you what is my personal motivation for being interested in this topic. I'm interested in this topic not only because it's my job or I teach it, but also because I've needed it at some point. So I try to get better at using programming for doing GIS. But I will talk more about that a bit later. Yeah, but I will be the only lecturer for this course, but I won't be alone. Luckily, there are 2 course assistants helping us. Emilia, who was also an assistant in the first period, she will continue working in this period as well. And then Ronnie Kurvinen will also join us as a course assistant in this period. So there will be only 2 course assistants. And same as first period, we are going to use Discord for communication outside class. If there is something urgent or if you can't reach us for whatever reason on Discord, you can of course email us as well. But Discord is usually more efficient. Yeah, so the course is scheduled. We will be meeting every week, same time. The time is very weird. Whoever decided that this course should be on Wednesday, 4 to 6 p.m. didn't like GIS probably. But yeah, this is how it is. So we are meeting from 4 to 6 or quarter to 6 every Wednesday. And each week we will cover a different topic. And I will talk about the topics a bit more later on. And each week we have an exercise. The only exception is week 6, so there is no exercise. You get a break from doing exercises. And that's if we are talking about OSM, getting data from OpenStreetMap. And we are meeting every week on site. The only exception is the 3rd week, which is, I guess, 12th of November. So there won't be any lecture on Wednesday. I will instead provide you with a recording of the lecture. And we will be more active on Discord in case you need support. But the help session will always happen every week. So that's the overall structure of the course. Yeah, and this is a new addition to the course. Actually, last year we did it for the first time. So this course used to, it was so that almost every year the Independence Day was overlapping with one of the lectures. So the course used to be most of the time 6 weeks. This week it's not overlapping with any of the lectures. So we have 7 lectures, so we are covering a new topic, raster data analysis. So this is the 2nd time we are teaching raster analysis with Python. Yeah, so I already talked about the lectures. They will happen here every week, except the 3rd week. And I will send more information about that later on. And we have the work sessions happening every Friday from 12 to 4. And the course assistants will be there to help you with your questions. So what are the learning goals of the course? after completing this course, you should be able to test and produce modular code, Python programs. So many of you, well, I will show you the survey results. Thanks for participating. Luckily, all of you are familiar with Python, and many of you have taken the course in the first period. So we are not teaching Python specifically anymore, but we are using Python to do everything we do in the second period as well. So you're just going to get better at writing code in Python. So yeah, so you will get better at producing good code in Python. You will learn to do GIS. And again, this is not a basic GIS course, so we are not really teaching GIS, but instead teaching you how to use Python to do GIS. So yeah, I don't think that's the case here, but if there's anyone who knows nothing about GIS, this may not be the right place for you, because we are not covering the GIS topics here necessarily, but we assume that you know GIS and we are doing it with Python now. Yeah, so and with GIS you have to deal with a number of things. Of course, you have the geospatial data. So we start talking about how to manage data. So different formats, how do you read, write, and then we have different kinds of analysis. You will learn to do many different things. We do map overlays, we do spatial join, buffering, network analysis, and many other things. And you will also learn how to create visualization. And we tried this, well, we didn't make maps in the first period, but we used matplotlib to produce visualizations. And now we get a bit more advanced. We produce maps, but also we learn how to produce interactive visualizations. And that's a major motivation for many of us who take this course. And in general, during this course, you will learn to plan and implement a geographical data analysis workflow. Again, all of us have some experience in GIS. And shortly, I will tell you why actually doing GIS in Python can help you become better at problem solving with GIS and designing better workflows. And of course, you will be doing exercises every week, and then you have the final project. So you get to practice this quite a lot. In addition to the GIS-specific skills, you will also hopefully develop some generic skills in this course. You will become more independent in searching for information regarding programming. This is something we have done and encouraged in the first period already. There are a lot of libraries, and this period we are going to work with even more libraries. Some of them have a lot of details, a lot of parameters. No one can remember everything. So one of the skills we develop is not to necessarily memorize everything, but rather be confident in finding information, whether it's from AI, it is from documentation or any other forums. You will get better at finding the right information. You will learn to apply new methods based on online documentation, critically evaluate the available methods and information sources, understand importance of version control. For those of you who have taken the course in the first period, you know that we do everything on GitHub. We use GitHub for delivering the materials every week. And we also use GitHub for doing the exercises and submitting them. So you will continue practicing work with version control, and you will get better at it. Communication is also important, and we do it through different ways, mainly through creating good visualizations and maps. And of course, hopefully we will be punctual, so that's another thing we will practice with submitting our assignments in time. Yeah, so this is the course evaluation. You will have 6 exercises accounting for 60% of your grade. So most of your grade is actually coming from the weekly exercises, and they are done individually. In the first period, we were doing things in pairs. In this period, exercises are done individually, but the final project can be done in pairs if you want. So that's one of the differences. So 60% comes from weekly exercises, 10% for each, and then 40% for the final project. And at any point, if you want to interrupt me and ask something, feel free to do so. Yeah, the due date for the weekly exercises is so they're published on Wednesday. The deadline is the next Thursday. So you have like 8 days to complete the exercise. And the final assignment is due on 7th of January, but I try to publish the materials earlier in December, so you don't have to I don't want to ruin your Christmas holidays. So I will share the materials with you early December, so you will have already time to plan it or even do it in advance. But the deadline is on 7th of January. And as I said, you can do this in pairs if you want. So every week we will cover a different topic. Today we already start with programming, doing things. So we work with geometries, the very basic concept when working in GIS, but important. So we don't get into GIS necessarily today, but we will work with geometry objects, points, lines, polygons, and we see how they are defined and how we can work with them in Python. From next week on, things get slightly more serious when we start working with GeoPandas. I've mentioned this already in the first period, and you probably can guess from the name. It's a library built on top of pandas, so everything that you learn in the first period, you're going to need them. So it's very similar. Almost everything is the same, plus some functionalities that allow you to do GIS, geospatial operations. So we will work with GeoPandas for doing a lot of things, starting from next week. And then on the third week, so we will use GeoPandas almost all the time for data management and analysis. But we have different topics covered every week. So on week 3, we work with geocoding and spatial queries. Yeah, that's very useful thing for many. For example, if you're working with different addresses and you want to get coordinates so that you can work with GIS, we will learn how to do that on the third week. Reclassification of data and or overlay analysis, week 4. Week 5 is about visualization. We will learn to make static and interactive maps. Week 6 is also particularly useful for many students and also for me. What I've learned from this, retrieving data from OSM. You know, OSM is, there's a lot of open crowdsourced geospatial data. Of course, you can work with the API, but on week 6, we will learn how to stay comfortably in Python, but at the same time be able to interact with the OSM API and get data. And we will use the data to do network analysis. And on week 7, we will work with raster, so basic raster operations. So use of AI is not allowed. So you cannot produce code by AI and just paste it in your assignment. But if you get help, as long as you're transparent about it, it's fine. So all of us use AI for getting help. If you have a problem, you want to help, you want to find the error, or with debugging, you might need help. It's all right to get help, but don't produce the results with AI. And as I said in the first period, LLMs are getting better and better, but they make mistakes, and some weird mistakes. So it's easy. Very often it's easy for us to tell if AI has been used. As I said, exercises are done individually, but the final assignment can be done in pairs if you want, but it's not mandatory. Yeah, so before we get started, before we continue, I would like to hear, there are quite many of us. So I would like you to introduce yourself very briefly, like in 10-20 seconds, tell who you are and what motivates you to be here other than getting the credits and finishing your studies. What is the major motivation for you for being here? Yeah. Nice to have you all here. You all seem to be in the right place and you seem very motivated, which is a great way to start this course. And we have, as you could hear, we have a wide range of students from different universities, even different countries, different backgrounds, so that makes everything even more exciting. Yeah, so a little bit about myself and what motivated me back in the days to get better at Python and use it for GIS. So I also came from master programming also. I came from a technical background, so I had some education in programming, mostly C++, like C-based languages, not so much in Python, C++ and C# back then. And although I came from a technical background, for some reason I had avoided programming for GIS quite well for a long time. Until later in my master's study and when I started actually my PhD, and I felt like, okay, I really need to get better at Python for programming. And what was the motivation? Well, the main motivation for me was actually automation, as many of you mentioned. So what I was doing in my master's and later in PhD was that I was working with PPGIS data. It's public participation GIS. So it's survey data that has coordinates. So people have marked places on the map and said, okay, I love this place, this is good, I hate this place. I know. So this kind of data. So the thing about this kind of data is that it's person-based. So you have like 2,000 participants in your data. So the usual GIS toolboxes were not useful for me anymore because I had to analyze something on a personal level. So if I have 2,000 individuals and I want to map their mobility, there's no toolbox in GIS, ArcGIS or QGIS that would allow me to do that. So I had to get better at automating things. So that was the major motivation for me back in the days, to be able to automate things. But also there are a lot of limitations in how we can do things. Like when you get a bit more advanced with GIS, when you are more confident in GIS analysis, then there are things you want to do, but simply there is no toolbox in it in ArcGIS. And do you want to be limited by what Esri is providing to you as a GIS professional? Probably not. So that's why that's another motivation for many of us who get better at GIS eventually and start using programming for it, not to replace the software necessarily, but it nicely complements the software. And you won't be limited by the tools that are provided to you. Another thing that was very important to me personally was that, but nowadays we use QGIS quite a lot, but back when I was studying, and that wasn't super long ago, like 10 years ago or so, ArcGIS was used quite a lot. And at some point I realized, okay, I have a master's degree in geoinformatics, and I'm so dependent on ArcGIS. What if Esri goes bankrupt? Like, am I out of business? And as a professional in GIS, you don't want to be dependent on a software. So that's another motivation for many of us. If you know how to do things with Python or any programming language, then you're in business, even if Esri is not. Yeah, so before I continue, a reminder, do the pre-course survey. Not only I will show you the charts from the survey to show you a bit more who we are, but also mainly I need your Discord name and GitHub usernames. And this has been a problem in last years. Some students, probably they're not here, those who don't come to the lecture. After 4 weeks, 5 weeks, they ask me, why haven't I gotten any grades from my exercises? Because you didn't tell us what your GitHub username is. So please fill out the survey if you haven't done so yet. Yeah, so many of you have taken the GeoPython course. For those of you who haven't, it will be nice to check out at least the topics, what we have covered, because the assumption is that everyone knows those things. So if you haven't taken that course, take GeoPython. The link is not here, but if you just Google GeoPython, it's usually the top result. So that's a good course to check out if you haven't done it already. 2 other courses that might be nice to take after this one. One is the cartography course that we have in May in the Department of Geography. So it's an intensive period. So it's 4 weeks. So it builds on what we learn in Autogis. So if you're interested in making even more maps, more beautiful maps, more advanced maps, in that course we get into cartography. And it is also an open course similar to this one. So from the website, you can just check out the materials, even if you don't want to take the course officially. There's another course in Aalto University, Special Analytics course by Henrik Tenkane. So that's also a good continuation after this one, if you haven't taken it already. Yeah, so before I show you the course environment, let's quickly look at the survey results. So previous night, have you completed the GeoPython? So as you can see, most of you have taken the first part, but there are some students who have not taken the GeoPython course. So I will give you a quick introduction of how this course works. All of you have used GitHub before, which is great. And all of you are okay or good with Python, which is, again, a great thing, and you will get even better at it during this course. Okay, so I will quickly show you the course's environment. Again, for those of you who have taken GeoPython, this is very familiar. So that's the course, the website, that's the course's website address, autogis-site.readtodocs.io. And every week we will publish the materials for the week. So now for week 1, you can see everything is published. And of course, there is some course information that is always there. So over the years, many people have contributed to this course. So what you see here during this course is the result of everyone contributing over these years. And this is an open access course, so there are people, we know there are people from around the world who are using these materials to teach GIS, and that's something we are very happy about. We will continue using Noppe, and all of you are students here, so you don't have problem with access to CSC, but especially for those who want to be watching this video later on from outside Finland, they may not have access to Noppe, but they won't have access to Noppe. Then the binder is also an option. Well, on the pages that there is code, there is a binder option, so you can launch the code live on the same page. Well, it will be a new tab, but you don't have to have CSC. Yeah, so I already covered the topics. I already talked about the general information, and there are some useful links here. Course environment, we will be using Jupyter Lab, and all of you who have taken the first period, you are familiar with that, so we will continue with the same environment. So you do not have to install Python locally. Of course, if you want to do that, that's a good practice. Like eventually you need to set up your own environment. So if you want to do that, you can practice already. But otherwise, everything is set up. All the libraries are installed on CSC Noppe. So you should be ready to go. Yeah, some information for those of you who haven't taken the first part course. Here you can find some useful information about GitHub and Noppe and Jupyter Lab. So check that out later. We won't use this voting so much. This course is not as big as GeoPython, so we can have just conversations instead of polls. And as I said, we will use Discord for our communications. I already talked about grading, so I skip it. We talked about learning goals. There is some information here about installing Python and packages. And we talked about use of AI and some extra resources if you're interested in learning more about certain topics. And that's all. So do you have any questions about the course, about the practicalities, or is it all clear? Okay, so let's continue with what we have for lesson 1. So what are the learning goals today? Well, first of all was the introduction to the course and knowing what we should expect from this course. We will learn a bit about Python packages that are available to us for doing GIS analysis. And we'll start working with one of them at least today. We will understand and describe how geometric objects, points, lines, and polygons are handled and stored by Shapely. It's the library that we are working with today. And we will learn to create geometries using coordinates. So that's the goal for today. We already talked about the motivation behind the course. Here there is a bit more information I quickly go through. Yeah, so for many of us, making nice visualizations is a major motivation. All of us have some experience with GIS, so you know that there is a limitation how much you can do in ArcGIS or QGIS. With visualization, especially if you're producing interactive maps, you know those software are very limited. So creating nice, advanced, interactive visualization is a major motivation for many of us. So by the end of this course, you will be able to make maps such as this one. Even better, more interactive ones. So you know that Python is not the only language used for doing GIS, but it's one of the major ones. And you may be asking why I should use Python for GIS. As I said, it doesn't really replace the software. It can if you want, but for most of us working professionally in GIS, it complements it very nicely. And So why would you want to use Python for GIS? As I mentioned, it's free to use. You won't be dependent on any software, either open source or commercial. So that's a nice thing. Another good thing, many of us who learn to do GIS with Python, after this you feel like you are even better at GIS. Even if you're not covering any new GIS topics here, you feel like you have better understanding of GIS. And the reason is that with software, it's just you have a toolbox, you provide input, output, and then you run the code without really thinking what is happening. But when you're doing things with Python, you know what's happening. You're in control. So after that, you have a better understanding of how things work. For example, today, like in GIS, very often you have not thought about geometries and how they're handled. You just import your shapefile or whatever vector data format and you start working with it. But today you will see that, okay, how do these work under the hood? So you will have a deeper understanding. Programming is efficient if you're working with large data sets. For example, if you end up working with big data, that's very common nowadays. You will see that with software you might have problems. So if you have like a huge data set of millions of points, there's a good chance ArcGIS or QGIS would crash unless you do it somehow efficiently. But with Python, you can handle large data sets. It's more flexible, as I said. The limit is basically how good you are at Python or how patient you are at things. You can do almost anything you want. And another nice thing is that you can combine functionality of different Python packages. So through this course, you will see there are a lot of useful libraries in Python, so you can just combine them. You can also combine it with QGIS and ArcGIS. You know that in QGIS and ArcGIS, you can do Python. So you can just extend what GIS provides you, the GIS software provides you by just adding Python to it. So a quick overview of the GIS packages that are available. There is a lot, and there's more coming all the time, and that's one of the nice things about Python. That it's a very vibrant ecosystem when it comes to development and libraries. For data analysis and visualization, NumPy is a general data analysis library, but also allows you to do a lot of things that are relevant to GIS. So that's very powerful. Pandas, we have worked with that. SciPy, Matplotlib for visualization, Bokeh for visualization, Plotly also for visualization. Those of you who later take the cartography course, we use this Plotly there. For GIS specifically, many libraries in Python build on top of GDAL. So it's a fundamental package for processing vector and raster data format. So many of them under the hood use GDAL. So we don't specifically use GDAL here, but there are a lot of things coming from GDAL. GeoPandas is what we are using. It's built on top of Pandas, and you know Pandas itself is built on top of SciPy and NumPy and many other libraries. So it's a very high-level library with a lot of dependencies. Shapely is a Python package for manipulation and analysis of planar geometric objects, what we will be doing today, and it's based on GEOS. We have Fiona. So Fiona is again included in GeoPandas. It allows you to work with different file formats, so saving, loading data, and you will see that. There are libraries specifically for working with projections in GIS, so PyProj is one of them. Again, GeoPandas is using PyProj for handling projections. PySal is a good library for doing spatial statistics and spatial analysis. I guess this is the library they use a lot in the spatial analytics course in Alto, but not in this course. GeoPy, contextually, we will use this later to add base maps to our map. So it's for visualization. And there are many other things. So there's Dash that works with Plotly. So if you want to make a website with Python with interactive maps, then you may want to check out Dash. So just without knowing any HTML or any web development skills, you can build a website with Dash and Plotly with maps. And many other libraries. So you can there are links here, you can check them out, and some of them we will learn. And as I said in the first period and also today, in Python environment, many things are connected. So rarely a library is working independently. So they're all connected. They use each other, like as dependencies. So this is an overview of some of the libraries commonly used in GIS and how they are interconnected. And a lot of the libraries have their fundamental underlying level in C languages, so very efficient. Yeah, so that was a bit more motivation for you. And now let's start the coding part. So let's start Noppe. Those of you who have not taken the first part course, you just go to noppe.csc.fi. It's a service provided by CSC, and it allows us to use Jupyter Lab online. So I have created the environment for you already. Everything is installed. Those of you who have joined the workspace in the first period, I think this should automatically appear for you, so you don't have to do anything. So now you have an Autogis2025. For those of you who have not taken this course before, I guess under course environment, if you scroll down and find CSC Noppe, you will find the code down here. So in Noppe, you just click on Join Workspace, and you just paste that code here. And once you do that, these two applications will appear, AutoGIS, GeoPython. Let's use AutoGIS. GeoPython was from first period. And once you have added it, just launch a new instance by clicking this power button. I have done it already. I have it open here. So do we all have Noppe working? Yeah. Okay, so for many of you who have taken the first period course, you will see that this is the same space. So you will see your files from the first period. So you have, for example, this notebooks folder. Depending on what you have saved there, you will see that. So to make sure things don't get mixed up, so let's just create a new folder here, call it whatever you want. I named it AutoGIS, so things don't get messed up. So as a reminder, anything that you save under my work will stay there. But if you save anything outside, next time you open an instance, it will be wiped out. So do not save anything outside my work folder, only inside this. So I created a directory called AutoGIS. I have already cloned the lesson. If you haven't, then now is a good time to do it. Just click on the plugin here. This is a GitHub plugin. You can also use the Linux terminal if you prefer, but this plugin is handy. Just click on it, clone a repository. And you need a GitHub link for this. And the link is again on the course's website somewhere. Okay. Yeah, if you just search for .git, you can find it easily. Yeah, so every week the lessons will be updated here. So just copy the link from here, paste here, and clone it. I have done it already. And then once you do it, you will have this notebooks folder added. And then we are ready to go. So are we ready to start? Okay, great. So let's just start with we have only one file to work with this week. Geometry objects. So as I said, we are going to work with Shapely library, the first GIS library we will be using in this course. And we will learn how to create and manipulate geometries in Python using Shapely package. So we are all familiar with GIS, and we know what kind of spatial data models. Well, now we are in vector world. We will deal with raster later. But in the vector world, you know that we will often work with, well, we will be working with points or lines or polygons. And to make things a bit more complicated, you might have multi-points that you're working with. So point means that you have 1 point per row in your data. Multi-point means that there are several points, but they are actually one row of data. So they're like considered as one feature. So this is a bit more complex format. Then we have lines. They can be a closed ring. They can form a closed ring. They can be separate lines and stored as multi-line strings. So a bit similar logic as multi-points. Same with polygons. We can have polygons that are full. They can have holes. They can have multi-parts. So we will have multi-polygons. So there are also geometry collections. So you have basically one row of data, but within that row you have different types of objects that you. So this is not super common. We will see how to work with this, but this is not very common, and it's often problematic in software, GIS software. It's not always supported, but that can exist as well in GIS world. It's a geometry collection. So all geospatial vector data can be described by combining a set of fundamental geometric objects. So if we learn how to work with points, lines, and polygons, we can just have control over our vector data. In Python, there's a library called Shapely that has become the standard tool for working with geospatial objects, and it's also the library that is used under the hood in GeoPandas. So even if we won't be explicitly using Shapely from next week, we are using Shapely without importing it explicitly. So Shapely, like many of the geospatial software like ArcGIS and QGIS, it follows the OGC consortium, the Open Geospatial Consortium. So it follows the same standards. So whatever you do with Shapely and in GeoPandas is compatible if you take your data just to another software. So that's also a nice thing. This is something I mentioned in the first period. We saw a data type called tuples in the first period. We worked with lists, we worked with dictionaries. We also saw tuples, but we didn't really work with them. So tuples are also a collection data type like lists, with the difference that they are not they are immutable, so you cannot update them. So you'll remember when you were working with raster, with lists, you could just update one item in your list. So you just go to index number 2, number 3, whatever number, and just update the value. The thing with tuples is that you cannot update them. And it has some benefits, for example, in computation. Well, it brings some safety. Your data is not immutable by mistake, and also it's efficient. So in world of GIS in Python, coordinates are stored as tuples. And tuples look like this. So there, you remember, lists are with these square brackets in Python. Tuples are with parentheses, and their items are separated with commas. So this is how coordinates are defined in Python and in Shapely. So I don't think I need to introduce what we mean by points, lines, strings, and polygons. We all know what we mean by these. With multi-polygons, in case you're wondering when you might need that, there are cases where you are showing something that might have multiple parts. For example, there is an example of a region in Austria where there's a gap between the two parts. So if you want to visualize this, if you want to store this in geospatial format in GIS, then you end up with two polygons that are separate. So do you want to have them as two separate rows in your data? Probably not, because it's the same area. It's the same feature. It just has multiple parts. So this is an example of a situation where you might end up with a multi-polygon. You might have polygons, we will see later, you might have polygons that have a hole inside. So an example of it is city of Espoo. So, you know, in the middle of Espoo, there is an area, Kauniainen, which is officially not part of Espoo. So if you work with the boundaries of Espoo, that is the kind of polygon you're dealing with. There's a hole inside. Yeah, so now let's get started. That was a bit of background. Now let's start with points, which are the most basic vector data types. So as usual, if you want to work with a library, you have to start by importing it. So I'm not going to import the whole library. Now I'm going to work with points. So from shapely.geometry, for now, I'm just going to import point. And note that the P is capital, so point with P capital. So it's a class under the library Shapely that allows you to define points. So we are going to import this class. And here is the part so that we create our point. So I'm going to create a number of points. So first one is point 1. And this is how you create a point. So remember that you imported the point class and it has the P capital. So the P is capital. And then you provide the coordinates. So you can try with what you want, but I have a couple of numbers here. So I'm going with 2.2 and 4.2 as my X and Y coordinates for the point. I'm going to create a second point and I'm going to call it point 2. And let's also create the coordinates tuple for it. So it's 7.2 as X. And for Y, I'm going to provide a negative number for a change. So 25.1 minus. Let's create a third point, and we are going to play around with this later on. So point 3. I go with 9.26 and minus 2.456. So we have created 3 points, and all of them are in the 2-dimensional space, so they don't have the Z coordinate. So I want to also create a fourth point called point 4. And this one is going to be in the 3D space. So I'm going to name it point 4 underscore 3D, so I remember what I have here. Defining it is the same way. So point, just remember that you want it to be in 3 dimensions, so you need X, Y, and Z coordinates. So 9.26 will be the X. Y will be minus 2.456. And for Z, I go with 0.57. So once you have typed in everything, just press Shift Enter to run the cell. And now the points should be defined. Let's try. So I'm going to write point 1 here and just run the cell. So this is a nice thing about Jupyter Lab. So if you have a geometry, if you have a geospatial data and you just put the name, it shows you the point or whatever it is. So I just wrote point 1 and it's visualized for me. But in case you're interested in seeing the coordinates, not the point itself, then you can just print it. So I will write print point 1. Let's also print the point 4, which was 3D. So point 4 underscore 3D. So if you use print, you can see that you get the coordinates. So you have the type of the object, point or point Z, meaning that it's in 3-dimensional space. And of course, you have the coordinates. So this format actually might be familiar to you. It's in well-known text format. I don't know, have you ever used well-known text format, or have you seen it somewhere? Sometimes you get GIS data that might come in this format, and QGIS handles it quite well. I guess ArcGIS struggles a bit. Yeah, and it's a standard set forward by the Open Geospatial Consortium. So the coordinates are visualized like this. Even if they're stored as tuples in Python, when you print them, you will see that they are in well-known text format, which is nice, following the standards. So let's try type. This is something we have done many times in first period. So I want to see what kind of data format I have in point 1. And you will see that it's a shapely geometry point. So it's a point defined by shapely. So this is long because it's the structure of the library, how it is defined. But essentially what this is telling you, this is a shapely point, and that's what we want. We have used shapely to create the point. So under the hood, shapely is actually using GEOS to handle geometry objects. GEOS is a powerful C++ library, so it's very fast and efficient. And it's one of the fundamental pillars of the open source GIS world. And it's also used in QGIS. So that's essentially what we are using when we are using shapely. Okay, so now we learned how to define points. Let's see some of the properties, some of the methods you can apply on the point. So one of the things you can do is to try to see the type. So of course you can do it the Python way, just write type point 1, what we just did, but you can also do it through shapely. So you go with point 1 geom underscore type. And it tells you that this is a point. So this is shapely's own way of checking the type of geometry. Yeah, so this is how we check the type. Another thing that you often need to do is to check the coordinates. So sometimes you need to do some calculations based on the coordinates in your geometry. And there are a couple of ways how to do that. One of them is using the chords method. So it returns to you a collection. So that's why I'm converting it to a list right away to make it easier. So I converted the output to list. And this is the method you use to get the coordinates. So point 1 chords. So as you can see, there is a tuple within a list. So if you want to access this item, you already know how to do that. So this is the index 1 of the list. From index 1, you want to access the index 1 within the tuple. So that's how you would access it. So you would go with point 1, index 0, index 0 if you want to get the first item. But there's an easier way for points to get the coordinates. And let's try that easier method. So you can go with point 1 dot x. And similarly for getting the y, you can go with point 1 dot y. And now that we are here, let's also print out the output to see what we are getting. So print x and y. So accessing the coordinates is fairly easy for points. It's not a point, name of the variable where you're storing the point, .x, .y, and .z to get the z coordinate as well. So now let's try it for the point defined in 3 dimensions. So it's the same. So x is from point 4 underscore 3D. This is how we had named it, .x. Y is 0.4 underscore 3D dot y. And z is also 0.4 underscore 3D dot z. Let's also print them out so we see what we get as the output, x, y, z. So accessing the coordinates of a point is very easy. It's also easy to use Shapely to calculate the distance between points. So let's check the input data. So remember what we have in point 1 and point 2. So these are the coordinates. And now we are going to calculate the distance between point 1 and point 2 and store it under a variable called dist, short for distance. So distance from point 1 to point 2. So point 1 dot distance and then point 2. And we already have a typed in f string here, which prints out the distance that you're calculating. So let's just run this. So distance between the 2 points, point 1 and point 2, is 29.72 units. So remember that Shapely geometries by design are agnostic, so they're unaware of the coordinate system. So because we just entered the coordinates, we didn't say, is it in meters, is it in degrees, is it in what coordinate system? So the Shapely itself is not aware of coordinate system. Later on, we are going to work with other libraries that handle the coordinate system for us. So now if you get distance with Shapely, Shapely doesn't know. If you happen to know this is in meters, yeah, the output is in meters. But otherwise, it doesn't know. And also, it's a Euclidean distance between point A and point B, so it doesn't take into account the curvature of Earth or anything like that. So it's very simple planar distance calculation. Later, when we learn about coordinate systems, we learn to do things more properly. Okay, so that was about points. Let's move on to the next object, and that's lines. So creating line strings objects is similar to creating points. Instead of a single coordinate tuple, we pass a list of coordinate tuples because a line is made of at least 2 points. And then you can use that to create your line. So for handling lines in Shapely, we need to import the correct class. So from Shapely.geometry, this time I will import line string, and remember that the L and S is capital. So line string. So now now that the library will be imported, I will use the library to create my line. And the way we create the line is very similar to points, except that it's a line string this time. And as you know, a line by definition is a bunch of points connected to each other, so you can use your points to create a line. So in this case, I'm going to use the 3 points we created earlier to create my line. So you can pass them in as a list. So point 1, point 2, and point 3. So this is one way of creating lines. So if you already have the points, you can pass them in as the list to the line string class, and it will create you the line. Another way of doing it is just by writing the tuples. So if you don't have the points already defined, you can just go ahead and type them in. So I will create a line 2. And this time I will just go with tuples for the different definition. So again, I will pass a list of my tuples, and I go with the coordinates of the points one by one. So the first one was 2.2, 4.2. You close the first tuple, move on to the next one, which was 7.2 minus 25.1. And the third tuple was 9.26 minus 2.456. Remember to close the list. So run the cell. So now we created the same line using two methods. The first one was through the points. Second one was just using tuples. Now I want to check if the result is the same. So I'm just going to write a conditional statement comparing line 1 and line 2, the two lines I created using different methods. And if you do the comparison, you get true, which means that the two lines are identical. So you can create a line using the points if you have them already defined, or just type in the tuples for the coordinates. Now let's take a look at our line. You remember, if you just put the name in Jupyter Lab, you get a view of the line. So this is what it looks like. And in case you want to see the coordinates, just print your line. Again, you see that it's coming in well-known text format. Again, let's check the type of data we have stored under line. It's a shapely line string. Similarly, you can check the type using shapely itself, so you can use geom_type. This will give you the same result, so it's a line string. So similar to points, line strings also come with a bunch of useful properties and methods that we are going to look at now. So one of the main things we want to learn how to use is to get the coordinates, of course. So let's get the coordinates and convert them to a list line dot chords. So this will return you a list of the tuples. So you have the tuples with the coordinates of each of your points in the line. So how to obtain the x and y coordinates? Here you have multiple lines. So with point it was simple. You would just say point.x, because one point has just one pair of tuples. There's just one tuple with x and y. With lines, as you can see, you have several tuples. You have several points. So you have to be more specific for getting the coordinates. So let's get the x coordinates and store it under x chords. And we can similarly get the y coordinates. Let's also print to see what we are actually getting as the output. So print x chords, print y chords, So this is the property that we are using. From line, you can get xy. The first index is going to give you all the x values. The second index is going to give you all the y coordinates. And you end up with two lists. We converted it to a list. So you end up with two lists of all the x coordinates, all the y coordinates. So if you want to access the second point's coordinates, then you know it's a list. So you can access index 1. So getting xy from a point was easier. But this is not difficult, but just, yeah, you need to be more specific because a line is more complex. Just remember that this xy method only works for x and y. So if you have a z coordinate, you don't use this. So you just go with the chords for that method. So xy is a shortcut for getting the x and y. So very often we are working with two-dimensional, but in case you have a z coordinate, then you just go with chords, and you end up with this, and then you can access the z. So the idea is the same. Just xy is for x and y. Okay, so let's explore a few other properties and methods of lines. One useful property is to get the length of your line. So I will store it under a variable called line underscore length. And getting the length is very easy. You just put the name of your line dot length. Then we have a f string here that prints out the output for us with 1 decimal. So the length of our line is 52.5 units. Again, remember, we don't know what is the unit yet. Sometimes you may need to get the center of the line, the centroid of the line, and that's also easy. You can just write line.centroid. So let's just do that and print the output. So I will just write line.centroid. And this gives me the center point of the line. So it just returns another point to you, which is the center point of the line.
Is this the point that's equidistant from like the beginning point and the end point of the line, or if it's like an arcing line, it's like not on the line?
It is on the line. It's based on the length, yeah. Okay, next object. Let's move on to polygons. So the logic is the same. Just the object is a bit more complex. So for example, for accessing the x and y coordinates, we have to work a bit more. But generally, the idea is very similar. So now we will work with a simple polygon without any holes. Later on, we will see how to add a hole to the polygon if that's something you need. So I'm importing the line, the right class. Everything is typed in. You don't need to type. So from shapely.geometry, I'm importing polygon with a P capital. I'm creating a polygon in a similar way. So for creating a polygon, you need to have at least 3 points to have a closed line. So, and you provide those 3 points as tuples within a list, similar to what we did earlier. So let's just run that cell. Similarly, if you have already points that are defined, instead of typing in the tuples, you can just provide them as items in a list. So this will create us polygon number 2. One thing we didn't work with, but what exists, and it's good to know about, is the linear ring. So if you have a line that is a closed line, so it's not a polygon, but a line that is closed, so it's a linear ring. So you can define a linear ring like this. So you import the linear ring class. here I'm defining a new variable called shell, and I'm defining a linear ring. So a linear ring is essentially made of points, with the difference that the point, the beginning and end is the same. So it starts with point 1 and it ends with point 1. So it tells Python that, okay, it's a loop, it's a closed line. So you can also use a linear ring to create a polygon. So we have 3 ways of creating a polygon. You just type in the tuples. If you have points, use the points to create the polygon, or if you have a linear ring, you can just use the linear ring to define the polygon. Let's just run this. And now, as you might have guessed, I'm going to compare the 3 to make sure what I get as the output is the same. So I'm comparing polygon 1 with polygon 2 with polygon 3. And it's true. So using these 3 different methods, we ended up with the same object. They're identical. Similar to points and lines and other objects, if you want to quickly view them in JupyterLab, you can just put in the name and run the cell. It will quickly show you what it looks like. So it's a polygon made of 3 points. You have ended up with a triangle. And if you are interested in seeing the coordinates, just remember that you can print the variable, and it gives you the coordinates in well-known text format. Similar to what we did earlier, if you want to check the type, you have 2 ways of doing that. So one is to use the Python way of doing things, so type polygon 1. And the other method was, of course, using polygon1.geom_type. Both of them are telling you that you're working with shapely polygons. And as a reminder, you can always, if you're stuck in an island without internet connection and you have only a laptop with Python installed, you can get the help without internet, so help polygon. So if you don't have access to documentation, you can always get help like this, so you know some of the things you can do with a polygon. So you can do the same thing with points and other objects as well. Yeah, so a lot of information here. So we are just covering a few things that are the most essential, but if you check the documentation, you will see that there are many other things you can do. Okay, now we want to define a new polygon that has a hole inside. So remember the example of Espoo and Kauniainen. So I'm going to define an outer polygon, and then I define a hole inside it. So I'm defining them as linear rings. So remember, it starts. I'm defining them as linear rings. Let's just run them. Now let's quickly see how it looks like. So I look at the outer. Outer is a rectangle. And then the inner hole is a trapezoid like this. So the units are not right. So the trapezoid is much smaller than that one. So don't judge the size based on what you see on Jupyter Notebook. So first I will create a polygon using the exterior shell only. And this is something we have done before. So I will create a new polygon called polygon without hole. And as we saw, we can use just the shell to create a polygon like this. Let's also visualize the output, so I will just put the name down here. So this is something we have done before. We have a polygon without any holes. So if you want to define a polygon that has a hole, so let's create a new variable called polygon with hole. You can define your polygon very similar to what we did before. So you define it by the outer, but this is the optional part. You can provide a list of holes that you might have in your data, in your polygon. So it can be multiple if there are like multiple holes in the polygon. In this case, we just have one, and we had previously defined it as a hole. So let's also put the name of the variable here to see what we have ended up with. So yeah, so now you created a polygon that has a hole inside. So let's print the variables to see the coordinates. And this is how the coordinates appear, again in well-known text format. The one without the hole is more simple. The one with the hole has more stuff going on. Similar to points and lines, there are some properties and methods coming in the polygon class, and you can see them here. So if you want to get the centroid of the polygon, you can just write polygon.centroid. If you want to get the area, again, we don't know about the unit, but you can get it using .area. If you want the bounds, the boundaries of your polygon, you can use .bounds. If you want to get this exterior, you can just use .exterior. And if you want to get the perimeter of the polygon, so you can get the exterior, and from the exterior, which is a line, you can get the length, like we did before. So you get the exterior of the polygon, and then you calculate the length, you end up with the perimeter of the polygon. Okay, so now let's take a couple of minutes. We don't have so much time, but let's take a minute or two to try this part. Check your understanding. Plot these shapes using Shapely. Okay, let's have a few minutes. Let's do this. So one quick thing about the interiors, we already saw how to get the exterior. With interiors, it's a bit more complicated. Not complicated, but you might, with exterior, you have only one exterior. You have one outer shell. With interiors, you might have multiple holes. So what you get, well, it's first of all interiors, not interior, like it's plural because it can be more than one. And what you get as output is some special sequence object. So the way to access it is to, for example, write a for loop. So I can write a for loop for I ring enumerate polygon with hole at interiors. Then I can loop through each of the holes in my data, in my polygon. And then I can print their number, but also access each of them. So you can access each of the holes as a ring, and then you can just save it as a line. You can get the length for it. You can do whatever you want. So if you want to get the interiors, you have to write a for loop to access each of them. In this case, it's just one. But if you had multiple, then you would have ended up with hole 1, hole 2, and get the circumference for each of them. And the polygons, did you get them right? Raise your hand if you got them working. Yeah, so many of you got it right. Nice. So I will skip it. Just remember, for creating a circle, you can use buffer. Later, we are going to use this for buffer analysis. So you have a point, you will use Shapely to apply a buffer of whatever radius to your point. So geometry collections, this is optional. So I will leave this to you. Everything is pre-filled, so you can just check this out on your own. Let's go to the last part, and that's creating a convex hull, an envelope for your data. But before we continue, let's run all these cells because we actually need them for the rest of the analysis. So this optional part. Let's run the cells. So we are defining a multi-point, a multi-line, some multi-polygon. Yeah, we are going to need the multi-points to apply a convex hull. So a convex hull refers to the smallest possible convex polygon that contains a set of geometries, for example, points. You sometimes need it, for example, if you're mapping the territories of animals. If you have a bunch of points, very often the convex hull is applied to get the extents. So you can easily create a convex hull using a multipoint. So you can just write multipoint dot convex hull. So this just applies a convex hull, a minimum bounding convex hull to your points. You can also apply an envelope. These are things that you might have seen in, for example, ArcGIS. There's a toolbox for this. So you can also apply an envelope, which is the smallest rectangular polygon around the geometry or set of geometries. So multipoint dot envelope. So this fits a minimum bounding rectangle around it. So yeah, so that was about geometries. One last thing we want to check. So, in the world of vector data, there are some topological rules that need to be followed, and Shapely makes sure that the things are valid. So there's a way of checking if your objects are valid, topologically speaking. So let's just write a print with f string. And I'm going to ask, is polygon valid? So this is the f string part. The actual part is here. So you can check if a Shapely object is topologically valid by writing polygon, but this is the name of your variable, polygon with hole. So I'm trying it for this one. You can try it for any of the shapes you created. Is underscore valid. So this is going to return a Boolean value to you. This I should have closed. So true. So the polygon is fine. Doesn't have issues. So this is just to quickly check that you don't have any issues. Okay, that was it for today. We learned how to work with geometries. From next week, it gets more fun. We will work with real GIS data. And remember that there's an exercise 1 already available. Yeah, and it works the same way as last period. Just accept the assignment. You will get a cloned repository, and you can work with it. And remember, we have a similar auto-grading system as the first period. So every time you push, for those of you who were not here, every time you push your changes to the GitHub, there will be a pull request with some feedback in the GitHub. So you get automatic feedback. And it doesn't matter how many times you push your changes, it doesn't affect your grade. So you can get immediate feedback if you want to just correct your. And this is the first year we have this auto-grading system, so there might be bugs, but hopefully it will work fine. Yeah, so see you next week.